For this lesson, you will need a CAP 697. We will look at each graph individually, starting with Section 2, SEP1, Figure 2.1, on page 3. Figure 2.1 is used to determine the time, fuel and distance to climb to a specified cruise altitude. Note that the distance given by the graph is nautical air miles. Therefore, the distance covered over the ground, nautical ground miles, must be calculated using the formula which was discussed in a previous lesson. An example of how to use this graph is shown, and the numbers used are printed in the top right corner. The example shown is rather comprehensive, so we shall only use a part of it. Our example involves a climb from sea level to 11,500 feet, where the outside air temperature is -5 degrees Celsius, with an initial climb mass of 3,650 pounds. Start by entering the graph from the left side of the baseline at the cruise level outside air temperature, in this case -5 degrees Celsius. In fact, the lines for our example are already on the graph, so we will be following those. From -5, move vertically upwards to the cruise altitude of 11,500 feet. It's not directly obvious where 11,500 feet is, so interpolate between the 10,000 and 12,000 foot lines to be as accurate as possible. From the intersection with 11,500 feet, go horizontally to the initial climb mass of 3,650 pounds. Then move vertically down to read the time to climb, fuel to climb, and the distance in nautical air miles from the three scales. The answers are 18 minutes, 6 gallons, and 36 nautical air miles. Having understood how to use the graph, let us now use the full example. Instead of assuming a simple climb from sea level to 11,500 feet, we will now assume we are climbing from an airfield at 5,653 feet to an altitude of 11,500 feet. The way to do this would be to calculate the time, fuel and distance to climb from mean sea level to 11,500 feet, which we have already done. Then calculate time, fuel and distance for a theoretical climb from mean sea level to the airfield elevation of 5,653 feet. And finally subtract the time, fuel and distance to climb from sea level to the airfield from the climb data from sea level to the cruise altitude. So now we start going through the graph again. Enter the graph at the airfield outside air temperature of 15 degrees and go vertically upwards to the airfield pressure altitude of 5,653 feet. Again, interpolate as best you can. From 5,653 feet, go horizontally to intercept the initial mass of 3,650 pounds. Then go down vertically to read the time, fuel and distance as in the last example. The answers this time are 6.5 minutes, 2.5 gallons and 12.5 nautical air miles. By subtracting these figures from the figures we found earlier, we can calculate the time, fuel and distance to climb from an airfield at 5,653 feet to an en route altitude of 11,500 feet. When you are ready to proceed, turn to Table 2.2.1 on page 4. The next set of tables on pages 4, 5, 6 and 7 deal with the recommended and economy cruise power settings. Each table has data for a different combination of manifold pressure and RPM. These are shown at the top of the page. First, select the correct table for the required power setting. The left-hand column shows ISA deviations for -20, 0 and +20. Select the appropriate block for the temperature being used. Enter the block at the appropriate cruising level. If necessary, interpolate to extract the required data. For examination purposes, it is not necessary to interpolate between the ISA deviation blocks unless the deviation is plus 10 or minus 10. So, for example, if the ISA deviation was plus 3, simply use the 0 ISA deviation row. Or, if the ISA deviation was plus 16, then use the plus 20 ISA deviation row. To interpolate for ISA deviations of 10, simply get the data for the ISA deviation of 0. Then get the data for the ISA deviation of 20. And then calculate the mean. To interpolate between pressure altitudes, a similar process is required. For example, to find the data for 7,000 feet, take the data for 6,000 feet, which is 26, then take the data for 8,000 feet, which is 22, and find the mean, which is 24. We shall use an example to demonstrate the use of the tables. Use the following figures. Cruise power 25 inches of mercury at 2,100 rpm. Cruise altitude 3,000 feet. Temperature plus 3 degrees centigrade. Calculate the fuel flow in gallons per hour. Now select the appropriate table for the power setting of 25 inches at 2,100 rpm. You should have selected table 2.2.2 on page 5, which gives the data for 25 inches of mercury at 2,100 rpm. At a cruise altitude of 3,000 feet and a temperature of plus 3 Celsius, the ISA deviation is minus 6 degrees. As there is no need to interpolate, we can enter the table at the ISA deviation 0 block. Cruise altitude is 3,000 feet, and therefore it is necessary to interpolate between 2,000 and 4,000 feet. The fuel flow at 2,000 feet is 10.7 gallons per hour, and at 4,000 feet 11.1 gallons per hour. By interpolation, the fuel flow at 3,000 feet is 10.9 gallons per hour. The indicated airspeed and true airspeed information is also available and can be similarly interpolated if required. When you are ready, turn to figure 2.4 on page 8. Figure 2.4 gives the maximum range of the aircraft in nautical air miles for different power settings. The figures make allowances for taxi, climb, cruise and holding fuel for 45 minutes. The example shown is a cruise altitude of 11,500 feet at full throttle and 2,500 rpm. Enter the graph at the cruise altitude and go horizontally to the power setting curve. From the intersection of the two lines, go vertically down to read the range in nautical air miles at the base of the graph. The answer in this example is 866 nautical air miles. The figures printed adjacent to the power curves are true airspeeds in knots. Using these figures and the forecast wind component, we can resolve the nautical air miles to nautical ground miles equation. When you are ready, turn to figure 2.5. The final figure in this section is the endurance profile. The endurance figures allow for taxi, run-up, climb, cruise and 45 minutes reserve fuel at economy power setting. This is known as the safe endurance. The data is entered in the same manner as for the range profile graph. Enter with the cruise altitude, go horizontally to the power setting curve, and then vertically down to read the endurance in hours and decimals of an hour. Although endurance is not affected by wind speed, the true airspeed figures are shown in the same way as in the range profile graph. Therefore, a calculation of nautical ground miles for a given endurance may be done. Let's sum up this lesson. For the single-engined piston aircraft, there are 4 basic graphs or tables. There is the climb, the cruise, the range graph, and the endurance graph. If the climb is from sea level to cruise altitude, the use of the graph is fairly straightforward. However, if the departure airport is not at sea level, a theoretical climb from sea level to the airport must be calculated, and the result subtracted from the sea level to cruise altitude climb. For the cruise tables, ensure that you are using the one for the right power setting. Interpolate for temperature only if the ISA deviation is exactly plus or minus 10. Otherwise, take the nearest. But interpolate accurately for altitude. The use of the range graph is straightforward. But again, make sure that you are using the right power setting. And remember that most of the time, the range will need to be quoted in nautical ground miles, not air miles. The endurance graph is also simple to use. However, the graph gives hours and decimal hours, not hours and minutes. And finally, remember that the TAS for range can be found from both the table and from the graph, and the TAS for the endurance can be found from the graph. This concludes the lessons on the single-engine piston. The next 2 lessons will be on the multi-engine piston, which you will find is very similar.